объявлений я возьму возможность поговорить по этому поводу. Первое, что по расписанию я должна была учить следующую лекцию, но так как некоторые из вас уже, наверное, знают, у Антония были небольшие проблемы с визами, это тоже, на самом деле, большая главная боль, и он не сможет приехать на следующих выходных, то есть его не впустят больше. И он не сможет учить на следующие выходные. И мы поэтому поменялись лекциями, и сейчас он будет читать лекцию, две подряд на свою тему, а я буду уже учить на следующих выходных. И приедет еще один преподаватель малого ТЦ, и он будет учить только этой специальности. То есть мы как бы разглашаем лекцию так. Следующее объявление. Мне сказали, что многие из вас хотели бы узнать более конкретно по поводу нашего университета и как подавать документы, и что это все значит. Но первое, самое естественное, если у вас есть конкретные вопросы, просто конкретно спрашивайте нас, и мы конкретно ответим на ваши вопросы. Но в общем и целом все очень просто. Если вы пойдете на адрес нашей кафедры, это просто вас приведет на нашу кафедру, и там вы сможете найти раздел «Академик». И в этом разделе там будет описание, как подавать документы на разные программы. Еще раз, программа, которую мы предлагаем, это бакалавр, мастер и PhD. Бакалавр это 3 года обучения, мастер это 2 года обучения, уже идет специализация на конкретные какие-то направления. И PhD это аспирантура. Чтобы подать на мастер, у вас уже должен быть диплом об окончании бакалавра, чтобы подать на аспирантуру, у вас должен быть диплом об окончании магистратуры. То есть 5 лет университета, или 6 лет. Университетов в России это 6 лет. Что надо сделать, когда подается? Там будет расписано очень конкретно на каждый уровень, какие документы. Но в общем и целом там надо заполнить форму. Просто распечатать и заполнить форму и расписаться. И там просто будет вопросник о вашей школе, о вашем университете, о том, какие у вас были проекты и так далее. Вам надо будет также приложить выписку из зачетной книжки, по-моему, это здесь так называется, ваши оценки, транскрипт. Вам, когда вы заканчиваете, вам выдается список тех элементов, которые вы закончили, и с оценками. То есть вам надо этот документ просто перевести на английский, желательно, в любом бюро переводов, и вам это переведут. На самом деле, сами можете перевести, просто в деканате поставить печать на выпуск зачетной книжки на английском языке, где будет просто список предметов, которые вы закончили, и ваши оценки. Следующий документ – диплом, копия диплома. Копию диплома несете в нотариальное бюро, и вам переводчик нотариально заверяет, что это настоящая копия, и переводит на английский. И вам надо также будет написать письмо, полстраницы, страницы максимум, почему вы хотите учиться. Почему вы хотите? Потому что мы, как правило, со всеми с вами разговариваем либо о мастере, либо о PhD уровне. Вам надо написать, почему вы интересуетесь graduate studies. То есть, когда мы будем на эти документы смотреть, мы просто сможем понять, вы действительно хотите учиться или это так, просто гулять. Вот. И последний документ – рекомендация. Вы можете попросить профессора или кого-то знакомого, научного руководителя, с которым вы работали, написать письмо, которое рекомендует вас для продолжения обучения. Что очень интересно, то, что вот мы будем с вами общаться, да, вы можете нас попросить написать эту рекомендацию. Если мы вас запомним, если мы будем уверены, что вы действительно хороший потенциал для нас, мы тоже можем письмо написать. Вот. Значит, это вот все достаточно просто. Если у вас есть вопросы, мы можем потом как-нибудь в лабораторию сходить, я могу на интернете показать, как это что делается. Еще возможность, так как мы здесь будем до конца следующей недели, то вы можете заполнить эти документы и собрать и отдать их мне. Я их отвезу нашему секретарю, чтобы вам не надо даже по почте посылать. Я могу просто ждать этот файл и... Чтобы, например, стать с нами аспирантом, вам надо дата, середина июня. до середины июня подать документы. По-моему, на мастера то же самое. Значит, все наши аспиранты получают зарплату, потому что они работают. Работать в аспирантуре – это работа. И они также помогают нам учить классы. То есть они работают с ассистентами в классах, они домашние задания проверяют, они общаются с студентами первого-третьего курса. Ну, а все остальное – это их научная работа. Обучение у нас платное для бакалавров и для мастеров. Там цена, на самом деле, совершенно номинальная, очень маленькая, около 2000 семестров. Но мы предлагаем 2 scholarship для мастера. Для лучших студентов, кто хочет учиться у нас на мастере, но мы можем дать вам scholarship. Okay, so are there any questions? Есть вопросы по поводу?
Вопрос, наверное, связан больше с призывом, потому что у вас...
С чем?
В армии. Принимают до середины июня, а диплом, скорее всего, будет у мастеров только, наверное, в июле.
Ничего страшного, это очень часто у нас так получается. Вы напишете, что диплом будет, что я заканчиваю, диплом дошлю. Я не понимаю, почему год? Почему надо?
Сейчас год у нас служба. Ну, если не принимать диплом до 15 июня, получается год, и это надо быть.
Еще раз, если к нам, вы можете просто написать, что вы дошлете диплом, и не надо помнить, какой гарантий.
Неправда, потому что никакой отсрочки ваша аспирантура, скорее всего, здесь не дает. Надо от нее убежать.
Я не буду по этому поводу комментировать. Вы уезжаете из страны, не находитесь.
Нет, говорят на самом деле, что можно договориться. Можно убедить свой автомат, что...
Еще вопросы? Очень хороший вариант для вас. У нас где-то 40-60 аспирантов. У нас очень большая научная программа, очень много аспирантов. И у каждого профессора, вот у Антония, например, Антония, how many students do you have? How many PhD students do you have?
Right now,
Yeah.
myself, I have 2.
Антония 2, Фернандо, how many PhD students do you have?
5.
Four.
4. Ну, достаточно много. У меня 3. И у других профессоров, мы можем не полностью наш профессор, у нас гораздо больше. У всех, у кого-то 10 студентов, у кого-то 2, 3, 4, 5 и так далее. И у этих ребят, у всех аспирантов есть свои web-pages. И здесь же вы можете найти людей, и там будет понятно, кто преподаватель, кто студент. Вы можете им написать и спросить, как там живется и как там учится. Они вам с их точки зрения могут дать советы о том, что стоит туда ехать, хорошо ли там и так далее. То есть я не уверена, что они скажут «да». Так что вы можете их задать по поводу жизни, по поводу работы и так далее. Еще вопрос есть по поводу поступления? И, значит, мы еще организуем в конце июня, начале июля летнюю школу. Школа совместно с американским университетом, Carzaniga университет, и наши преподаватели. И то есть там будет смесь преподавателей. Это будет продолжаться неделю, 5 дней рабочих. И мы приглашаем вас подать заявление. И у нас есть тоже гранты на то, чтобы людям помочь с финансовой точки зрения. То есть, чем быстрее вы подадите, там надо просто заполнить application форму. Там тоже надо, чтобы ваш руководитель или там, преподаватель написал письмо, чтобы мы знали, что вы достойные люди. Вы, например, можете написать, что вы взяли вот эти курсы с нами, и мы уже будем знать, что вы достойные люди. Раз вы во время выходных приходите учиться, это уже значит, что вы серьезно к этому относитесь. То есть это совершенно реально, мы можем помочь. Вообще не будет регистрации, то есть это будет бесплатно. Ну, в общем, это для осознания.
На какую тему школа?
Школа Dependable Computer Systems. И 6 лекторов будут читать лекции на разные 6 тем. То есть если у нас есть линк от нашего кафедры, вы можете почитать, там есть абстракции. Я буду учить, Анна будет учить, Маур Цет будет учить, и будут преподаватели Дэвид Гарланд, Билл Шерлес, тоже в Carnegie Томас Росс, он историк, но у него тоже позиция двойная в Carnegie в Америке. Вот, то есть вы можете почитать, о чем он говорит.
А это только для студентов или...
Это открыто и для профессионалов, и для студентов, и так далее. То есть у нас приходят из индустрии тоже люди.
То есть, грубо говоря, если я не студент уже лет так 8, я должен мучиться совестью про себя говорить или не должен?
Нет, не должен.
Спасибо.
So I guess that's all I covered. You probably can tell.
Yeah, I understood a couple of words. That's all you could say. Carnegie Mellon, that's what you said. A couple of times.
Можете сказать пару слов о том, как будет экзамен проходить, потому что все спрашивают, что это про это.
Значит, экзамен будет 3 мая. Экзамен будет принимать 2 человека. Я и Марк, да? И мы вам выдадим вот через Сашу просто лист вопросов, которые будут просто покрывать все лекции. И вы придете, у вас будет какое-то время, там, полчаса, 45 минут письменно ответить на эти вопросы, а потом мы просто будем параллельно с Маурой с вами разговаривать. Вы будете отвечать на эти вопросы, которые вы уже готовились к ним. И мы потом у вас соберем ваши письменные вот эти ответы, то есть достаточно важно, чтобы это было в нормальном виде, потому что потом эти же ваши ответы будут читать Фернандо и Антонио, и они вам уже будут звонить тем, кому они посчитают нужным из ответов, и по телефону с вами разговаривать, так как они не могут сами присутствовать, то есть они потом некоторым из вас будут прозваниваться. Вот. Ну, вот такого формата будет экзамен. Понятно? Хорошо. Okay, I think I'm done. So take the advantage and talk to all of us while we are here. This is your best opportunity to establish the connection and to see if there is a mutual interest to work together. We are here to find people to work with, and you are here to find people to work with too, right? So this thing. Don't be shy, talk to us. As long as you want, express your interest in a particular topic. We will just see if it's workable, if we can essentially figure it out how it can be done. Done?
Well, I just want to express my interest in
Okay, good. So when you think about a PhD, you probably think about a particular area you're interested in. So because you have to figure out a particular professor you would like to work with, and to talk to this person about your interest. So it's a good idea to start thinking in this direction. Thank you for doing it. Okay.
Okay.
So I will pass it.
Okay. Welcome back to those who had the guts to come back. So my plan today, as you probably figured out, I didn't get a visa to come back here, so that's why I'm now talking about 2 things in this entire afternoon. So what I want to do is to go back to finish our discussion about the transport layer, about reliability. Actually, that is done. Congestion control, and talk about TCP a little bit. And then after that, and maybe it's more than half of today's lecture. Hopefully, I will talk about my research. So I will give you a presentation trying to highlight the area. One of the areas, the primary area of research that I'm working in. So if you're interested, if you have good ideas, maybe we can start talking about it. And if you're interested in pursuing a PhD, maybe you can talk to me. And if you find these things interesting, maybe something will work out. Okay, so actually, I don't remember this is going to be. Let me see here. See, we have 216 pages. Actually, you can't see it. All right. Let's see, let's try this. There you go, this one. Let's try this. Much more. 50. Okay, let's start from here. Okay. Do you get it? It's going to go this fast for the entire day. Okay, this is all stuff that we've seen. Let's see. Okay, so we started talking about congestion control, right? You remember the analogy of the kitchen sink. We have these routers, and routers have these queues of packets. And when you start having more inflow than outflow, then the queues start filling up. When they fill up to the point where there's no more space, the router essentially has to throw away the packets. So that's why the internet loses packets. It's not a matter of the wire is not working. It's the routers losing packets. It used to be one day, there's errors on the wire. No, these days, routers lose packets. And that causes congestion. Why? Because you have more and more losses force the endpoints to retransmit, and so people keep insisting, the border of the internet, keep insisting on putting traffic inside while traffic is already being thrown out because the routers are full. So we'll talk about that. That thing is called congestion, how you avoid it. And as we already said yesterday, the way to avoid it is to
do nothing. Not to send.
Not to send.
Do nothing.
It's to slow down effectively. So the way to avoid congestion, just like in the car, if you want to avoid a congestion on the highway, don't drive. That's easy. Right? So to discuss that, I wanted to. I'm hoping I'm not insulting you. This is really not serious math here. It's just. Okay, so the total latency, when you send a packet to a router, the router takes it, processes the packets, and then sends it out. And the total latency, meaning the time it takes for the router to do all of that, is the sum of essentially three components. The transmission time. This has to do with the physical medium. Okay, maybe Ethernet takes some time, optic fibers takes another time. Then there's the CPU time, that's the processing time, how much the router takes to process the packet, to figure out where it needs to go, for example, to look up the forwarding table. And then this one. This one is the queuing time, how much time the packet spends in a queue. So think of this as the post office. So you go to the post office to do something, or you go to, I've been told, I don't know if this is true, I can tell you it's true in Italy. There's a lot of bureaucracy here in this country. And so if you go to a public office, maybe, to get a document, say, you spend some time doing that. And so there's the time it takes you to get in and out of the office. That's pretty short, as we know. There's the processing time. The actual time it takes for you, if you're at the post office and want to send a letter, for the clerk to stamp the letter or to read okay, it's going to St. Petersburg, okay, it goes to that queue, figure out the cost, and you pay. Okay, that's all, CPU time. And then there's the queuing time, and that's the overwhelming part of the majority of the time that you spend in public office, because you sit in a queue for hours, right? Why? Because there's a very long queue. So in fact, the delta queue is proportional to the length of the queue, and it's inversely proportional to the throughput. So if the office can serve, let's say, 50 requests in an hour, and there's 100 people, you sit in line for 2 hours. Okay, this is what this thing says. Okay? If we can do 50 an hour, and there's 100 people, then you sit in line for 2 hours. That's it. Okay, if we understand that, then we can start comparing this, plugging this function, or plugging the parameters of the input into that function. So let's look at that. Let's look at the ideal case first. The ideal case is an ideal case where this office, again, let's say it's a post office. There's lambda n is the number of people that walk into the post office per time unit. And T is the throughput. It's how many they can be served in the time unit. So if lambda input, the amount of people that walk in, is less than the amount of people that can be processed in that time, what is the length of the queue? Zero, right? Well, maybe there's some bursts. Okay, lambda is not constant. There's some bursts, so the queue can absorb the bursts. Okay, it's like a spring. It compresses little things a little bit. But in general, there's no queue, right? Because everybody that gets in can be immediately served, and they can be served faster than the speed at which they walk into the door. That's the ideal case, zero queue length. What's the extreme case? Well, the extreme case is where you have an input flow that is higher than what the office can process. So you have accumulation. You have accumulation of people in queues. And the accumulation, so the length of the queue, grows with time. Why? Because if I can process 10 per hour and 15 people, 15 people per hour walk in, then I have an accumulation of 5 people every hour. Okay, so the queue grows by 5 persons per hour. That's what this formula says. Okay, the queue, length of the queue is proportional to time, and the factor by which it grows is the difference between the throughput and lambda in. Okay, so again, if 15 people walk in every hour and the office can serve 10, then you have a queue that grows by 5 people every hour. So this thing says. And so if we plug in that, then this is the delta Q. Again, notice that all these things are parameters, they're constants. The killing factor is this. It's proportional to time. So what this says is, if you want to go to the post office, go there early in the morning. This is what this formula says. Okay? Because the delta Q will be proportional to time. Because obviously they process not fast enough. Okay? So if you get there at the end of the day, you also get the entire line formed during the entire day. Okay. So if you look at the effect of that formula on routers and congestion, you have those two extreme cases, the case where it's zero and the case where it grows. And so if you look at steady state, meaning effectively at infinite time, what do you have? Well, you have a situation.
Can I a little question?
Yeah.
Isn't this the ideal case when lambda in is equal to T?
No. That's sort of the borderline case. That you are using as much of the throughput as the office can
But the
give you.
queue doesn't increase.
Let me go back a second here as soon as I find out. In this case, less than, I should say, or equal. Notice that there's no equal in this one. It's sort of the borderline case. Okay, where you're using just as much. You know, you're dropping people in the queue and you're taking people out of the queue at the same speed.
So this ideal case is...
It's not ideal.
Because we haven't
It's
been increasing on the queue.
It doesn't matter.
In theory, you're right. This would work exactly
Like this.
with an equal. In reality, this is what I was going to say. Let me
In
go.
extreme case,
No.
delta
It
Q
isn't
will
the
be
extreme
0.
case.
In any case.
No, only ideal case. Because in extreme case, we, by definition, we have the increasing of the queue.
Yeah, 0 times whatever, and it's 0 still. What's the difference? I mean, the border case, you can call it whatever you want. You have delta Q0.
Think of that really simply as I have an input flow and an output flow.
Okay, it's not a big deal.
Okay? No. Let's talk about it. You have an input flow and an output flow. When do you have accumulation? Again, think of water going into the sink, water going out of the sink. If you have a smaller flow for input than output, then there's no accumulation. Then you can turn on the knob and add more water.
When you have exactly the same input flow as the output flow, you still have zero accumulation. Okay? Because, as he was saying, this difference is still zero. But as soon as you cross the line, okay, that go above, as soon as the input is above the capacity, the throughput, then you have accumulation. And you have accumulation that is linear. So this is there's a discontinuity. Okay? In fact, what I was going to show is this. The ideal case is this. At steady state, you have 0 delta Q, 0, 0. This is lambda. This is your accelerator. That's how much traffic you pump into the network. So this is your accelerator. You turn it on, turn it on, turn it on. At some point, this thing shoots up. Okay? Because this is at infinity time. This is a steady state. Okay? In fact, there is no steady state when you have more input than output. Why there is no steady state? Because the queue keeps growing as a function of time. Right? How does the post office solve this problem? They close at 5. If they didn't close, you would have lines growing forever, right? I don't know. Do they close at 5?
So it's better to go in evening actually, to be the first in the morning or night day.
Right. So I told you, go there first thing in the morning. This is the theoretical case, you realize, right? Because even if you wanted to augment to increase the input, these things are not constant. There's always jitter. There's variability all the time. Okay, so it's not true that there's no queue. Sometimes there's more people because maybe that's when the bus comes by and all the people that get out of the bus, they wanted to go to the post office. You have 5 people that walk into the door at the same time. So you have a queue of 5 just at that time. So it's not true that it stays 0. The reality is that you have variability. So you have something more like this. The queue length starts at 0 and it's small and it stays small at steady state. When you approach, again, this is the accelerator. So you're accelerating, and this is the queue length as you accelerate. At this point, the system breaks completely. It cannot serve requests. That's when you have congestion. So if you look at this from the perspective of the delta Q, this is the graph. If you look at this from the perspective of what can be served, the throughput, this is the graph. So you have the delta input, this is your accelerator, once again, and this is the delta, I'm not saying delta, you should correct me, lambda input, and this is the lambda output. So this is the throughput, how many people successfully get their letter mailed. Initially, it's linear. You accelerate. Think of this as a car. Again, you accelerate, the car accelerates. You accelerate a little bit more, the car accelerates. You get to a point the car doesn't accelerate. At least my car, doesn't accelerate. After a while, it's sort of. But networks, unlike cars, have this destructive behavior. That at some point, it's not that you keep accelerating and there's no more juice in the engine. So the velocity will stay constant in my car. In networks, you have this destructive effect. You keep pumping traffic, and this traffic ends up destroying, making the network collapse. In this situation, that's when you have congestion.
Sir, could you please remind the precise meaning of lambda out?
Lambda out is the effective number of packets that get through the network, that gets delivered. So I am sending messages to you.
The effective number or percentage?
The throughput. Its number, the unit, the dimensionality of this is number of packets per time, per unit time.
So how it can decrease? Anyway, it will stuck on some level.
No, that's exactly the point of congestion.
In that meaning, it seems that maybe I missed something, but in that meaning, throughput won't decrease. It will stuck in some level.
What I'm trying to tell you is that the analogy with, say, a physical system like an automobile, a car, driving, doesn't work.
I understand.
Things at some point explode, in the sense that, like, your engine goes too fast and it breaks.
We don't care that people who are waiting for hours in that queue. Anyway, our output, speed of our processing is maximum. Then there is some queue actually.
No. Let me explain why.
A post office serves.
Yes, the analogy works up to a point. In the case of the post office, it might work. In the case of the internet, with transport protocols, the way that we've seen that before, doesn't work. Why? Imagine the whole transport protocol. What do you do? Consider, say, stop and wait, or go back in. Let's say go back in. Okay. What do you do with go back in? You send something and you wait for acknowledgements. Okay. Maybe a packet gets lost. Maybe the acknowledgements get lost. What do you do in that case? There's a timeout and you resend the whole set. Okay? Maybe the packet gets lost. Maybe the acknowledgements gets lost. And so what do? You resend the whole set. So you can get to a point where you keep sending and resending, trying to get that information through, and you don't get it through. So it could be the case that zero information gets through, because there's so many full queues that either the packet or the acknowledgement get lost. Is that clear?
In that case, it's clear.
Yeah, that was the point. If you try to compensate for the network being slow or unreliable by pushing more traffic into the network, you get to the point where pushing more kills more. And so you get to the point where you are less effective even.
Yeah.
So,
but it seems that the reason for that is we are considering a long term of communication. I mean, if we need to send only one packet, it's extremely good idea to send one packet. It's a good idea for everyone to send this packet in that period of time. If you don't care about, if you don't care callbacks and other protocol-specific details. So it's in TCP situations, it's bad idea to send simultaneously. But maybe in some other protocols, maybe
yes, but consider another protocol. Forget go back in. Have you ever heard of a protocol? The protocol that is used for wireless networks, that is used also for cell phones. Okay, it's called CDMA. Okay. Yeah. Typically, what you do, let's do a simpler version of that. Do you understand what I'm talking about? Okay. This protocol can be played in a room like this. Okay. So let's say that in this room, I don't want to do it now because immediate congestion. Everybody that has to say something to their friends, they just yell. Okay. So if I, what's your name?
Yuri.
Yuri. That's easy for me. Yeah, thank you. So, if I want to say something to Yuri, say I'm going to send him a little message, and I would say, Yuri, I'll see you tonight at 10. Okay. If there's silence in the room, you can hear the message, and the information got through. But if at the same time somebody else wanted to send a message to some other person, they would yell it, and at the same time you have collision, and neither of those two messages would get through. If the protocol is simply to repeat the message, you have instant collisions, congestion. And the more you insist, the more you have congestion. You realize that because you keep repeating. I keep saying, Yuri, I'll see you tonight at 10. And somebody else says, Sasha, let's go out to lunch tomorrow. And we keep saying that, and nobody else at that point can use the medium. So you have zero communication. Okay, this is exactly the same curve that you see in a wireless network. Typically, you have, if you use this admittedly stupid protocol, you have exactly something like this. After this point, things start degrading, and you have congestion. And so, in fact, even in CDMA, there's the CD part. There are carriers. CDMA.
Condition detect.
Detect, exactly. Carrier detect. You hear, before speaking out, and this is what people do in a room typically. You don't yell if somebody else is already yelling. This is what you do. And so that avoids some of the congestion. But still, it gets bad. So, in fact, in those protocols, you have what's called an exponential back-off. You slow down. The first time, you slow down by a certain amount of time, random. And the second time, you slow down by an increasing exponentially, meaning multiplicative amount of time.
In Ethernet, as I know, in Ethernet technology...
it's exactly the same. It's exactly the same behavior. Because Ethernet is a shared medium protocol. So.
Important point in Ethernet is to shut up for a random time.
It's to shut up. Exactly.
Yeah, it's not decreasing. It's a random, just random period. So, but when there are lots of hosts,
it is increasing. It is random, but it's increasingly long. Okay, and this is the same thing that you do. We'll see. That's exactly what TCP does when it tries to cope with congestion. So what do you do? And before that, I wanted to. So what do? You slow down. You remove traffic, and so you'll see that slowly but surely things start to improve, and you reduce congestion at that point. Now, to deal with TCP, I wanted to briefly introduce TCP. Well, you probably know all of that. Who does not know anything about the TCP protocol? Let me ask a different question. Who knows what the congestion window is? Okay, 2 people know what the congestion window is. 3, 4, 5. So let me give you a brief introduction of TCP. What's that?
The RFC numbers.
RFC numbers. You want the RFC numbers? I don't know the RFC numbers. I haven't written down because I don't know the RFC numbers. So just a little bit of terminology. TCP is a transport layer protocol. So at the transport layer, we call the data units. We call them segments. We don't call them packets. I always mistakenly call them packets anyway. So forgive me if I do that. And there's 2 important numbers. One is the maximum segment size, which is the maximum size of every segment. And this depends on the technology, on the underlying link. And then we have the maximum transmission unit, which is exactly the maximum unit of data that can be transmitted over a specific link. So, for example, if you're using a network like Ethernet, anybody knows what the maximum
1,500 without Windows XM1.
Wow, he knows everything. Okay, yes, it's 1,500 bytes. Okay, so you have a maximum transmission unit of 1,500 bytes. Okay, so those things are useful. We'll see why they're useful. What's that?
It's not true.
It's not true. Now it's not even true. It's almost true. Like everything I say.
There is a jumbo frame technology that allows the big Ethernet packets.
Really?
Like up to 64Ks.
Wow. I did.
And it is supported in modern network.
Really?
Yes.
Wow. Even my computer?
No, it's Dell.
You've been criticizing my computer. That's okay. I'm not married to Dell. Whatever. Okay, so just briefly, this is the TCP header. There's a few things that are important here. There's many things, and they might sound confusing. There's just a few things that are important here. Source port and destination port, you should know what they are, so I'm not going to spend time. So these are the 2 most important pieces. Okay, the sequence number, the acknowledgement number. These things are the equivalent of the numbers that we were attaching in go backend to every packet. Remember, 1 blob, and so on. And then there's a bunch of flags, and you know, so there's a SYN flag, the FIN flag, and the acknowledgement flag. And this, the receive window. The receive window is the receiver telling the sender to slow down because the receiver cannot read enough, fast enough. Okay. But essentially, the two things that I wanted to point are these two. Okay, sequence number, acknowledgement number. These numbers allow TCP to work pretty much like go back in, with a small difference. Actually, let me pause for a second. Do we have, how much time do we have? We stop at 5. Is that true? At 5? And we'll have a break in the middle, maybe 10 minutes at some point? Okay, good. Okay, and I'm not going to really spend too much time talking about those. You'll find them in the slides if you're interested, but you find them in a book also. A good networking book will have all of this. So I don't want to spend time doing this. I just wanted to talk about the sequence numbers. In TCP, sequence numbers, contrary to go back in, do not identify packets. They identify bytes. So a sequence number in TCP says, in the stream of data going from A to B, I am acknowledging or expecting byte sequence number 75. Okay, that means that I already received up to 74. Up to 74, it's the decreasing sequence. No, up to 74, and I am waiting for byte number 75. Why do we have two numbers? Why do we have the sequence number and the acknowledgement number? Maybe you can infer that from what I just said.
I don't know actually. I just guess to support duplex channel. Maybe.
Exactly right. Exactly right. So TCP is implementing what amounts to a duplex channel. There's two streams of data. So there's a stream going from A to B and a stream going from B to A, and the acknowledgements are numbering or referring to the numbers in the opposite direction. The sequence numbers are referring to the numbers in the direct direction. So let's just look at the sequence numbers with this example, and there's another example coming. Let's say that you have 4 kilobytes of data that you want to send, and you divide that in maximum segment size of 1 kilobyte each. So, you know, the sequence of the first one, starting from, let's say we start from 1, is 1, and then the last byte of that chunk is 1024. So the first byte of the second chunk is sequence number 1025. The first byte of the third chunk is 2049. Okay? And so when you send things, you will see those numbers in the sequence number of the packets going in that direction. So if you send a packet, there's this piece of data. This is the bytes from the original 4 kilobytes data. You put this in here, and you add a Tcp header. And in the Tcp header, if you remember, there's those two numbers, right? There's the sequence number and the acknowledgement number. And the sequence number of that packet is going to have a number in it. What is the number of the sequence number in that Tcp header?
2049.
Huh? 2049, exactly, because it gives the number of the first byte in the stream of data going from A to B. As I said, there's a stream of data going from A to B, there's a stream of data going from B to A. So how do you deal with that? Well, you deal with that with acknowledgement numbers. Okay, so acknowledgement numbers tells or give the sequence number that you acknowledge in the opposite direction. And acknowledgements are cumulative. So let's go with an example. So the first example is this. There's a packet going from A to B, and it has sequence number 1200, data size 1000. Okay, so that's the amount of, it says The first byte in the payload of this is byte number 1200 in the stream from A to B. And this packet contains 1,000 bytes. So what do you expect the next packet going from B to A to say? Huh?
We have received up to 2,198 bytes.
Right, so then you are acknowledging, yes. So the next packet says, oh, I gave a better example. So let's say you get that one, so what's the acknowledgement going back in the other direction?
For the first.
Well, cumulative, so you always acknowledge everything, the last thing you see. So what are you going to acknowledge here? Is that right?
The first not received.
You actually acknowledge the first one that you have not yet seen. Okay, so you acknowledge 2700. Okay. Yes, so you acknowledge 2700. Right? Again, the sequence number is the sequence number of the packet, of the stream, of the byte in the stream going from A to B. When the packet goes this way, this is what you find in the acknowledgement numbers. Okay. This is just the stream going from A to B. What about the stream going from B to A? Same thing, right? I didn't say anything about this sequence number. Okay. In fact, we'll see that as an example. There's two streams. Let's consider a simple echo application. What's an echo application? You send a byte, and it gives you back the same byte. It's a ciao, ciao. Okay, so ciao, you send a C. So what's the result of that?
Acknowledgement and C.
Good. So what's the acknowledgement number coming back?
The number is 199.
1.1.
That's a big C. 101, so 101. And what is going to be the sequence number of the C going in that direction? Who knows? That's exactly the right answer. We don't know. I know. So let's say it's 200. So as you can see, this packet is acknowledging 101, which is part of the stream going from A to B, and it's sequencing 200, which is part of the stream going this way. These two numbers are unrelated. Completely unrelated. There's no relation whatsoever between the sequence number of the stream from B to A and the sequence number of the stream from A to B. Absolutely no relation.
In actual echo application, they will be relevant, of course, because this is the same topic between.
In the echo application, they will be augmenting in log steps. That's true. That's true. So you will always see, correct. Although, if some packets get lost one way or the other, so again, the sequence number of this, we're saying ciao. Now we're sequencing the one that we were acknowledging before. It was sent byte 100. Now we're sending byte 101, and we're acknowledging 201, meaning that we saw 200 and we're expecting 201 from the opposite stream. So if you understand this example, this is how acknowledgements work in TCP. Okay, and obviously that's the other way around. And the term that is often used is that acknowledgements are piggybacked on data packets. Piggybacking means, you know what piggybacking means? I guess pigs do that. I don't know. They go, you bring somebody on your shoulders. And so I'm the big guy and bring somebody along with me on my shoulder. So the big packet here, data packet, is piggybacking the acknowledgement of the opposite direction. So if I go in direction A to B, I'm also piggybacking an acknowledgement of the direction of B to A. Okay, so I don't want to spend too much time on this. But TCP has the same reliability schemes that we've seen for Go Backhand and all the others. If somebody doesn't get acknowledged in time, then there's a timeout and there's a retransmission. And the question is, go backhand had a fixed timeout. TCP, on the other hand, has to adapt to all sorts of different channels. With a long timeout, with a short timeout, with a long latency, with a short latency. So it has to have an adaptive timeout. So the question is, how does TCP choose the timeout? It tries to adapt it to the round trip time. Why? Well, if your timeout is, let's assume that your timeout is shorter than the round trip time. What happens?
No communication.
You keep sending. You get tired to wait before the actual time it takes for the acknowledgement to get to you. So you assume that things are lost, even though things are not lost. Okay. So that's bad, because you keep replicating things. I mean, you don't replicate, but you send a lot of extra crap. What if the timeout is too long? What if the round trip time is 1 second and your timeout is 10 minutes?
Sitting around.
Huh?
Wait and sitting around.
Yeah, you sit around for 10 minutes just to figure out that one thing got lost. Okay, so you want to adjust the timeout as close as possible to the round trip time. And so the question is, how do you do that?
You measure?
It's written.
Measure the time.
Yes, you do adaptive sampling. I mean, you do adaptive timeout. So the timeout is measured because how can you measure the timeout? Well, the protocol already has acknowledgements. You can use them. You can start the clock. You send a sequence number up to 200 and waiting for acknowledgement of 201. If you correctly receive 201, you measure the time it took. And then from those measurements, you try to guess what the next round trip time is going to be. And how does TCP guess? It uses this thing called exponential weighted moving average. It has a previous estimate, and it has a measurement, a sample S of the round trip time, and so it gives some percentage of the weight to one and some percentage of the weight of the remaining weight to the other. Okay. And if you see what this does in terms of how it follows the signal, if you look at this as a signal, how it follows the signal, it essentially smooths the signal out. So it tries to follow the signal but smoothing it out. I don't know if I have one. So if you have the actual samples, this is sample times. And let's say in black I have the samples. So you can sample here, sample there, sample here, sample there, sample here, sample there. What is your estimate? Well, if you combine them, it's something that goes a little bit in the middle. So, you go from here, then you go from here, then you go here, and then here, and then here. Right? So it's sort of smoothing things out as opposed to this. Right? So this is the actual signal, and the red signal is your estimate. It's sort of a smoothed out version. And that's what TCP does. It uses this exponential moving average. Not only it estimates the round trip time, it also estimates the variability of the round trip time.
Why the TCP uses such kind of filtration code? There are lots of algorithms.
To do estimations?
Yes.
I don't know. It's one as good as the other. It doesn't have to be that sophisticated. Meaning, you're not trying to predict the stock market. You're trying to predict. No, I'm serious. These things are physical systems many times.
Actually, the stock market predicting moving average exponential is widely used too.
Yeah. Any economists in the room? Economists don't have a clue.
Forex.
You an economist? No.
No. I just played on Forex.
Foreign exchange market.
Oh, Forex, foreign exchange market. Okay. No, don't. It's, at that point you might as well go gamble, horse racing. At least it's fun. These things, the point is that you have something that has maybe a lot of variability, and you don't want to trust every single sample. You want this thing to follow the signal, but not to trust every variation of the signal, because those things have maybe high variations. In fact, if this is the timeout, you never want to underestimate the timeout. You want to stay above the signal. So what do? You take this, the estimate, let's say the red one. You take the estimate of the variability. Okay, let's say that this is plus or minus this. Okay, and just to be safe, you establish something that is maybe twice as much. It's this plus twice the variability, so it's right here. This is how TCP does it. Okay, so it estimates, it uses a timeout that is up here. Why? Because you want things to vary. Maybe the next thing is going to go boom up to here, and you want to still catch it, but you want to stay as low as possible. Okay, so that's how TCP does it. It's just a choice. Again, it doesn't have to be too sophisticated because, if it misses something, it's okay. Okay, so this is something about TCP. I really don't want to spend too much time on TCP because I want to talk about language detection. Let's see. Connection setup. Everybody knows about how TCP establishes connection, right? SYN, SYNAC, back. You all know? No, I wasn't. Sorry, it wasn't you, but. So there's this thing called a three-way handshake, and the purpose of that three-way handshake is to do what? Is to establish the sequence numbers. Because we have to know what the sequence number is, right? The first time. So we can acknowledge each other's packets. So there's a packet that goes out from the client. Now we don't call it A and B, we call it client and server. Client is the one that initiates the connection, server is the one that accepts the connection. Client sends a packet that has the SYN flag with its own starting sequence number. Server replies with another packet that contains the SYN flag and also the ACK flag because it's acknowledging the sequence number of the client. And it also contains its own sequence number. And so that also gets acknowledged by the client to the server. So after this three-way handshake, if everything goes well, then everybody knows, the client knows the server sequence number, the server knows the client sequence number, and we can start chatting. And then the finalizing of the connection is similar, and this is a state machine that represents it. I really don't want to spend my time on this. Okay. Go back to congestion control, which was the more interesting subject. How does TCP deal with congestion control? The main idea, as we said, is to slow down. So all you want to do is to reduce traffic. And so there's a few questions that you have to answer. First of all, how does the sender measure the status of the network? If I want to slow down, if I'm driving on the highway, congestion control in this case means you don't want to hit the guy in front of you. You want to maintain a certain distance. So the first thing you have to do is have to have eyes and measure the distance between you and the guy in front of you. So the question is, how does TCP measure the status of the network? If there is congestion, I need to slow down. If there isn't any congestion, I can accelerate. But I have to figure out if there is congestion or there's no congestion. Issue number one. Issue number two, what are my accelerator and brake pedals in TCP? I need to accelerate if I want to accelerate. I need to brake if I need to brake or decelerate. What is the pedal connected to? How does it work in TCP? Sending rate. there was no parameter in the TCP header that said sending rate. The window size. Remember, also in Go Backend, we had that window, and as long as we have empty slots in the available, remember, it was the pending ones and the available ones. As long as I have available slots, I'll keep sending. So effectively, the length of the window is a measure of, how far I'm pressing the accelerator. Okay, so the window size is going to be that. And, okay, so now I have eyes, I have a pedal. Now I need to learn how to drive. I need to modulate. I see congestion, what do? Slow down, how much? So I need to modulate the output rate in some way. So there's those three questions. The first two are sort of technical and easy to answer. Actually, the second one is very easy to answer. The first one, not so easy to answer. But, okay. How do you detect congestion? So, eyes. What are the eyes of TCP?
Round trip time.
Round trip time. No.
Packet loss rate.
Packet loss is a good one. Why?
Delays between acknowledgements, for example.
Delays between acknowledgements. That's a measure of losses, right?
Well, it's not. If the network is very, very fast, you get one acknowledgement. After that, you send 1,000 packets, and you get another one. The delay between acknowledgements is very long, but the network is very fast.
That's not completely true. But in any case, the point, I think the most correct answer is those two are measures of the same metric. How many packets am I losing?
Yeah, for good networks, it's a good measure, and for bad, it doesn't matter because we don't know their
right.
loss.
So what's the other measure? I mean, we know when we lose packets. How do we know? Remember, how do you detect that you lost something? The real answer is you don't. Okay, but you have a timeout. Okay. Confused. So I'm sending you traffic, and I'm the sender. I want to figure out that there's congestion between you and me. If you send me,
why not use just rate of lost packets?
How do I know?
Resend packages.
Huh?
And resend packages, lost acknowledgements which didn't reach us.
Us, the sender.
Yes. So we can measure our lost acknowledgements.
Yes.
We send something,
yes.
Acknowledge something, and receive the same thing back because the other side thinks that it was lost.
Good. Okay. So those are the two. So there's duplicate acknowledgements and there's timeouts. Okay. Duplicate acknowledgements means I'm sending something. The receiver sees that it's out of sequence. So we didn't go through this, but the slides that I flipped through very quickly. If there's one that says sequence number 1, let's go with 1, 2, 3. Sequence number 1, and then sequence number 3. Oh, missing sequence number 2. What does the receiver do in that case? The receiver re-acknowledges sequence number 2. So it tells the sender, hey, I'm still waiting for 2. You sent me 3, but I'm still waiting for 2. Okay, so receive 1, acknowledge 2. Receive 3, re-acknowledge 2. Okay, so this thing is called duplicate acknowledgement, and it signals a loss, right? It tells the sender that some packet got lost. Okay, that's one case of a lost packet. The other case is you just don't hear from the receiver. Send something to him. Receive nothing. Try sending me mail. You won't receive. I don't use email. And then you don't receive a response, and after 2 days you say, what's the deal? I sent you an email yesterday or 2 days ago. Okay, so timeout. Duplicate acknowledgements and timeouts. Those are the two ways that we have to know that something got lost. What do they represent? They represent different things. In the case of To duplicate acknowledgement, at least I got the acknowledgement. It means the network is not completely hosed. It's not completely broken. Because at least the duplicate acknowledgement got to me. Okay. So that is a serious problem, but not as serious as timeout. Timeout is silence. You know, sending things, as they say, crickets. You say something and there's silence in the room. Okay, so those are the two metrics. Duplicate acknowledgements, which are bad but not as bad, and timeouts, those are bad. What's the mechanism? As we said, it's the congestion window. So those are our eyes. Our eyes are duplicate acknowledgements and timeouts. Congestion window is the pedal, is the accelerator. How do we accelerate? We enlarge the congestion window. How do we decelerate? We shorten the congestion window. And if you remember, go back in, it's the same exact thing. So I'm going to go flip through this. It's actually, this is a little technical, but it's really stupid. And so this is the third and most important question. Now we have eyes, we have an accelerator, we learn how to drive. How do we drive? And so this is how TCP, the interesting things about the development of TCP, there's many versions. I don't know if you know that these TCP, different variants of TCP have different names. So, and I think they're named after cities in Nevada. Because gambling is legal in Nevada, I guess that's why. And so this is a form of, trying to guess things. So there's Reno, and there's Las Vegas, and what else? There's not a lot of cities in Nevada. It's mostly desert. So how does this work? How does the modulation work? Well, it works according to essentially three principles. The first principle is what's called additive increase and multiplicative decrease. What that means is that when you drive, you accelerate linearly. So there's a linear acceleration. You see that there's a road, empty road, empty road, and you say, okay, I'm going to accelerate linearly, so, with a constant acceleration speed. And then you see a little bit of red lights at the bottom. What do? You decelerate very quickly. So you decelerate multiplicative decrease. That means that you decelerate exponentially. Boom, slow down. There's congestion over there. That's principle number one. There's another principle which, in my opinion, this is the official name. It's called slow start. In my opinion, it should be called fast start. It's counterintuitive to me. We'll see why. What is the problem when you accelerate slowly? We were talking about this yesterday. What's the problem when you accelerate slowly? That if you have a very fast connection, it takes time to get to the speed, up to speed, the speed that you can exploit the connection at. So you can exploit the connection at a speed that is very good, and because you accelerate slowly, it takes time to get that speed. So this slow start is the process by which you actually start and try to go very fast. Okay, so in the initial phase called slow start, because you start slowly, you accelerate exponentially. So there's a first exponential acceleration, which is actually the same thing that you try to do when you drive. You're at a stoplight, red, turns green. What do? Go as fast as you can. Then then you get around the speed limit and try to slow down. And there's a different way. This is what I was talking about. There's a different reaction to timeout events than you have to double acknowledgement events. We'll talk about that. So there's these three principles, and I don't want to spend too much time, so I'll explain those with examples. Okay, the rule is this, actually. The rule of as I said, it's a ramp, okay? So it's reduced, at every loss, TCP is reduced by reducing the congestion window to a half. So effectively, your speed goes to half every time there's a congestion in distance. And when you increase linearly. So there's a ramp, and then there's the exponential decrease. So it looks like something like this. You know, you increase, accelerate. The window is a measure of the speed. Okay, so this is your speed. Okay, so acceleration, linear acceleration. Speed grows linearly. And then something happens. Boop, and you half the speed. Accelerate, boop, half the speed. Accelerate, half the speed. Okay? That's how it works. What about slow start? Okay, slow start is this process where you start from one MSS. So you start by sending one MSS and waiting. MSS is the maximum segment size. Okay, this is the number of bytes that you send the first time. So effectively one packet. And then wait for the first acknowledgement. So in the very first step, TCP looks like which protocol? You remember?
Something and wait.
Stop and wait. Exactly. Stop and wait. Stop and wait. So send a packet, have to wait. So you want to accelerate fast at the beginning. So you start from this very, very low speed, and you proceed exponentially. So if you, I don't have the example here. Okay, I have the example later. So hold your thoughts. Now there's a different way that we deal with NACs. NACs are duplicate acknowledgements. Okay, so if I send an acknowledgement twice, that's equivalent to sending a negative acknowledgement. So NACs are treated differently from timeouts because timeouts indicate congestion in a deeper sense than NACs. As I said, if you do get a duplicate acknowledgement, that means that the network at least was good enough to send you the duplicate acknowledgement. If there's timeout, meaning there's silence, things might be really bad. So you do these two different things. In the case of a timeout, in the case of a 3 duplicate acknowledgements, it means that, alarm, something got lost, is one thing, and in the case of a timeout, you do different things. So in the case of a timeout, you go all the way back to the start and run slow start at the beginning. So you go back to the bottom. You go back to one MSS and then ramp up. You ramp up with slow start, which again means fast start, exponentially until you reach the half of the window size that you had before the timeout. And then proceed with congestion avoidance. Congestion avoidance is the linear ramp. So you go back to 0 effectively, go exponentially up to half the speed that you had before, and then proceed linearly. This is what you do when you have a timeout. And when you have a duplicate acknowledgement, so a NAC, or a triple repeated acknowledgement, which is a NAC, you just simply slow down by half. Okay? And so here we go. This is the final example. So you start from 0, 1 MSS, you ramp up exponentially the first time, and you stop whenever you hit the wall. So you say get a NAC at this point. What do you do when you get a NAC? Half. Okay? So you go half the speed, and then you ramp up in congestion avoidance linearly. Let's say there's a timeout. What do you do with a timeout? All the way to 1 MSS, and then what? Exponential up to half of the original, and then linear. Okay, and then let's say that there's an NAC over there, you go to half, and so on. Okay? That's what TCP does. And it's a game, right? You're trying to accelerate, and then, get a slap in the face, and then, okay, I'll slow down. And then, sneak in a little bit of acceleration, and then you get hit. That's what TCP does. Okay. This sort of concludes my planned lecture on the transport layer. Let's see, let me wrap up, and we can, obviously, I'm happy to discuss with questions if you want to talk about this. So we looked at 2 aspects of the transport layer. We looked at reliability, and we looked at a very easy protocol, stop and wait. looked at a little bit more complex protocol, go back in, another protocol called selective repeat, and a concrete, very real protocol used on the internet called TCP, and how they deal with reliability. And then we talked about congestion control. And congestion control is the process by which the queues and routers fill up, and at that point the routers have to drop packets, they have to discard traffic, and that causes other people to the extreme, at the end of the network, to throw more traffic, trying to pump more traffic through, and that destroys the network. So to avoid congestion, you simply slow down, and I talked about the mechanisms that TCP uses to slow down. How it detects congestion with naps and timeouts, how it can accelerate using the congestion window, and how it actually does it, how it modulates this process. Slow start at the beginning, congestion avoidance, slow start, congestion avoidance, and so on. In fact, those are, what you can see, there's a slow start phase, congestion avoidance, slow start, congestion avoidance, and so on. Okay? Do you have any questions on this? Or no comments? Ideas? Yes?
For example, a question. Can we change something in the receiver's behavior?
Can you change the way the receivers behave? Is it legal? No, I think the police will show up and then you have to pay somebody. I'm kidding. What do you mean, can you change it? Of course you can change it. There's implementations of these things. Your computer is running an implementation on the TCP stack, and you can change that implementation if you can change the operating system. But it's not that complicated. In fact, there are variants of TCP that try to be smart. They try to be faster, out-gamble and send, not a slow start, but super fast start. I'll start up immediately to a maximum size or something. You can change it, and it probably won't cause major problem. If everybody on the internet changed it to be very aggressive, then yes, you'll see more congestion on the internet. That's the way it was before TCP was developed. You didn't have the precautions in the implementations of senders and receivers that TCP has, and that caused congestions on the internet. Did I answer the question? No. Sort of? More or less.
Actually, I have an idea after his question. It will be quite interesting to change TCP implementation on, for example, your computer and computer of other side to be more aggressive, because in common TCP implementation, after some bottleneck, it will decrease exponentially, as we see. Yeah. And if we will, in the next second, minute, it doesn't matter. The load won't be bottleneck really. Mm-hmm. It shouldn't be bottleneck because aggressiveness was dropped up by a factor of 2 at least. Mm-hmm. So if we will change, it's kind of cooperative game. It's the question of game theory maybe in some point of view. Because if we will change, only we, you and I, will change it.
Because we are the only smart people in the world.
If we will change implementation, our connection will be faster actually.
In reality, as I said, that's the possibility. You can change it. I can change my operating system. In reality, I don't think you get really a significant gain.
No, it seems I will get an advantage. But if all the people will change that.
That's not even necessarily true. In say, direct connection between you and me, there might be congestion between you and me, okay? And the congestion might be on your end, on my end, somewhere in the middle. Even between you and me, it's not true that because only we are using that connection, that there will not be congestion. I mean, rephrase, because it might not have been clear. Even if the only 2 users of the internet were myself and yourself. Okay, so Yuri and Antonio are talking, nobody else is speaking. Even in that case, there might be congestion. And even in that case, it might make sense to use to back out. Let me give you another example that maybe will clarify the situation. I'm sure you all use peer-to-peer systems, or some of you have used peer-to-peer systems to download movies, other things that I'm not going to mention. Okay. Is that? I'm not going to say. YouTube. Okay, those systems have rate control. Say BitTorrent. Okay, you use BitTorrent, right? So BitTorrent has rate control. And you can configure BitTorrent to rate limit your upload, because typically everybody has a contract with an internet provider where the download is, it's an asymmetric connection. Certainly if you have technologies like cable internet, the download is usually much higher than the upload. Now, have you ever tried pushing it above the limit? It breaks. It just simply breaks everything else. And the fact that it's not adaptive, that itself, it doesn't slow down. Or maybe it does slow down, but it's slow in slowing down. It's not as good as TCP. You cannot effectively use the internet. You, at that point, are experiencing, even locally, just by yourself and your internet connection, you're experiencing congestion. And so all your application, you can't access the internet, things are slow, so you keep hitting reload on your browser. Damn it doesn't work, And the more you do that, the more you create, you think you're, I'll reload. The system is, you should slow down. Even if you think that by being aggressive, because, hey, I'm smart, Yuri's smart, the two of us can talk, nobody else can be as smart as we are. And even in that case, you hit congestion.
Do you exist any statistics or something for the following thing? We have a congestion in the network and something like half of the packets are lost.
Yes.
What we do, first one, we overflow the network. So for everybody, the window is very, very small now.
Okay.
And after that, we stop sending the direction and start sending the right traffic. And at that moment, we are the only guys who are sending loads of traffic.
Yeah, it's exactly.
Right. So this is network, terrorism. Everybody's shut up now because something bad is going to happen, and nothing bad happens. Because usually that's the case, and then you say, "No, I am the real guy." I'm sure there's all those tactics, but again, you should view this as an engineering. Enterprise, try to engineer the system so that, and also to not just to be fair, but to make the system resilient to failures. Again, if you try to be aggressive in that case, and then of course, it's not that just the two of us are smart. Everybody in the room can say, "Oh, I want to be smart as well." They all download the smart version of the protocol, and before you know it, the network collapses because we're all so smart that the network fell apart. So, again, this is engineering. It's the same, another thing that comes up, it didn't come up here, but oftentimes when I teach this, some of the students would react and say, "Oh, can you just avoid the congestion by routing around the congestion?" So with the analogy with traffic, you're on the highway, there's a congestion, what do? You get off the highway, go on the small roads. Right, like you're the only smart person that got off the highway. So typically what you do is you get off the small road and you're stuck in the same congestion, only now with only one lane, as opposed to 2 lanes or 3 lanes. So, you can try to be smart, I guess, but the final lesson is other people are smart as well. And so, it typically doesn't work if you think that. If your system relies on the fact that you're smart and nobody else is,
what's the state of the congestion situation in current networks? I mean, there are some articles which try to frighten everybody and say the internet will collapse Just because we have lots of
No, I think the internet is very solid right now. There's ways to make it collapse that are different. It's corrupting the routing infrastructure, either maliciously or just by mistakes, or the good old physicality of it. If you have a big wire that goes under the Atlantic and you cut it, you cut the wire. There's no repeat and go back in that can save you from that. But no, I think, in fact, the backbone of the internet seems to be, it's all fibers. And they say that those fibers are mostly dark, meaning they're not used to the fullest extent. Now, with P2P systems and people transferring DVDs all over the place, but most of the traffic carries probably video signals for cable operators, for television operators. Or voice for voice over IP, and I should say I'm not an expert in that. I don't know enough about it. But my guess is that the internet right now is over-engineered for that. Doesn't mean that it will last forever. As they say, the typical example is wait until 1 billion Chinese get a cell phone. Yes, of course. If 1 billion Chinese turn on their cell phone right now, probably the internet goes down. But it'll be engineered to sustain that, I guess.
And when we'll see IPv6 in action?
Oh, it's in action already right now. And
that it's not in action.
It will. In fact, cell phones are probably the primary drivers for that. You will see that the standard for cell phones and for internet over cell phones and for voice over internet over cell phones are for IPv6. And so that'll be a major factor. Also, more things to worry about in the world, but to the extent that that's your worry, Okay, so let's pause maybe for 10 or 15 minutes, and then we'll start again and talk about research. Okay.